you quickly run into a problem. X-rays at these wavelengths have enough energy to eject electrons from their atoms, so most materials absorb them. But unlike medical X-rays, which have wavelengths shorter than 1 nanometer, these are still long enough to interact with air, so air absorbs them too. That meant that Kinoshida's setup had to be in a vacuum. But even worse, he couldn't use lenses to focus the light, because the lenses would absorb it too. So it seemed like this idea would never work.
But around 1983, Kinoshita stumbled on a paper by Jim Underwood and Troy Barbee. Their work focused on special mirrors that could reflect X-rays with a wavelength of 4.48 nanometers. So Kinoshita was intrigued. Curved mirrors can focus light just like lenses do. If he could figure out how to make these special mirrors for the wavelength he was using, then this could be another way to do photolithography. The mirrors work something like this. When light crosses from one medium to another, say from air to glass, it bends or refracts. Some of it goes through and part reflects back. How much gets reflected depends on things like the angle, the light's polarization, and most importantly for us, the difference between the refractive indices of the two media. The larger that difference, the more light is reflected. And Underwood and Barbee used that principle. They made a super thin layer of tungsten, less than 1 nanometer thick, thin enough that X-rays could pass through without immediately being absorbed. When X-rays hit the layer at a specific angle, the tungsten reflected less than 1%. Then they carefully tuned the layer thickness so the path length of the transmitted X-rays was only 1/4 of its wavelength. Then they added another layer, this time out of carbon. It has a higher refractive index than tungsten for wavelengths of 4.48 nanometers. The X-rays hit the boundary and a little bit more reflects. But this time, the phase is inverted, or it's changed by half a wavelength. This happens when any light moves from a lower refractive index to a higher one. Now, by the time this new reflected wave reaches the tungsten boundary, it has traveled another 1/4 of its wavelength, for a half wavelength in total. So the two phases line up, and the waves interfere constructively. Underwood and Barbee kept doing this trick for a total of 76 alternating layers, so that in total, they could reflect back much more of the X-rays. Now, they only managed to reflect around 6% of the light, but it was a proof of principle that you could reflect X-rays.
So Kinoshita saw the possibilities. He got to work, and after around 2 years, his team designed and built 3 tungsten carbon curved multi-layer mirrors to reflect 11 nanometer light. And with it, he managed to print lines 4 microns or 4,000 nanometers thick, proving that, at least in theory, X-ray lithography was possible. A year later, in 1986, he went to present his findings to the Japanese Society of Applied Physics. Proud and excited, he explained his setup and showed his image. But to his horror, the audience refused to believe it.
Unfortunately, the audience was highly skeptical of my talk.
Kinoshita was devastated. He later said, "People seemed unwilling to believe that we had actually made an image by bending X-rays, and they tended to regard the whole thing as a big fish story."
Nobody believed that this was a viable way forward, and unfortunately, the reaction was at least somewhat justified. First, this light isn't naturally produced by anything on Earth. The closest natural source is the sun.
We had to basically build an artificial sun here on Earth.
Most scientists, including Kinoshita, produced X-ray light using a particle accelerator or a synchrotron.
It gives an enormous amount of power. It's as big as a soccer field. You can fuel a whole fab. The problem is if the light goes out, the whole fab goes out.
So each machine needed its own power source. But even if you could produce the light, you'd need to make incredibly smooth mirrors to actually focus and print those tiny features. You would need the smoothest objects in the universe.
Okay, so I got a football, and I've got a bouncy ball, and a cobblestone street. Now, what do you think is going to happen when I drop them? The football basically bounces straight up, but for the bouncy ball, it just shoots off to the side. And that's because the surface is relatively flat for the football, which is much larger, but it's super rough for the bouncy ball. And a similar thing happens with mirrors. If the surface is super rough compared to the size of the wavelength, then the light scatters randomly. Now, it might look smooth, but if you zoom into a mirror, you find something that looks like this. You find all these crazy bumps. And now to measure the roughness, what you do is you take the average of these bumps, And that will give you your mean line. Now, for a normal household mirror, the average height is about 4,000 silicon atoms. But for Kinoshida's mirrors, which not only needed to reflect X-ray light, which has 100 times shorter wavelength, but also needed to minimize scattering, so that all the photons make it onto the wafer, it needed to be way more smooth. It needed to be atomically smooth. In fact, the average bump could only be about 2.3 silicon atoms thick.
If one mirror would be the size of Germany, the biggest bump would be about 1 millimeter high.
But Kinoshita refused to give up.
However, my belief did not change.
And soon, help would come from an unlikely place.
Across the Pacific, around 70 kilometers east of San Francisco, is Lawrence Livermore National Lab, a lab that was born out of the Cold War, heavily funded by the US government and built for one purpose and one purpose only: nuclear weapons. The lab was founded by the inventor of the cyclotron, Ernest Lawrence, and the father of the hydrogen bomb, Edward Teller. And over its lifetime, they designed over 10 fusion-type nuclear warheads.